There. Good morning. Happy Tuesday. I'm running a little bit late today. That's okay. We're on a new section today, so I'm looking forward to that. We're starting chapter 7. So you had your quiz, and like I said before, so if you go through, because I have been finding that it's it is marking some correct answers as incorrect, so definitely make sure that you go through and check those. I had some emails and I've made those adjustments, but make sure, because now that the quiz is closed, you can go in and you can check your work and you can check your answers, right? And not until it's closed. So make sure that everything is kind of looking like it was marked properly, and if not, then let me know and I'll have a look. Okay. So same thing, right? We're going to start chapter 7 today, and then we're going to have a quiz on chapter 7, and that's going to be our last quiz, right? So you've had all these quizzes, and we're kind of zeroing in on material as we go. Okay, so I don't really want to do a review because you've already had the quiz. And so I'm just going to get right into chapter 7. I guess I said that, but I really do. I'm fighting the urge to do a review, right? But so chapter 7 is called Inference for Numerical Data. Now, it's not until you've seen a lot of this stuff that you start to pick up on the hints in the names and in all these words. And so I want to kind of pick it apart so that it makes maybe a little bit more sense to you, right? So inference is this umbrella term for confidence intervals and hypothesis testing. Okay, so inference is confidence intervals. And hypothesis testing. What you'll find is that the procedure that we follow for each of these will stay the same from chapter 6, which was inference for categorical data, right? So in 7.1, we had inference or 6.1, we had inference for one categorical variable, right? So one proportion. And then we moved into how do we compare two sample proportions? And then we moved on and we said, okay, well, what if I have more than two sample proportions? Then what can I do, right? Then we went from a Z-score, so a Z-test, to a chi-squared test, but the procedure stayed the same, right? So we're going to introduce another test statistic today. It's the t-test statistic, so the t-test, which is probably the most common thing that you're going to be doing out in the real world, okay? And it is for numerical data, right? And so we kind of built up these skills using proportions, and then finally we finished with, okay, well, what if I have two categorical variables and I'm allowing them to have as many categories as they want to have, right? How can I test if they're dependent or independent of each other, right? So it's kind of a quick recap of chapter 6, but now we're going to do something similar for numerical data, okay? And so numerical data, right? So now we're going to be talking about the means instead of proportions, right? We were testing proportions for categorical data, right? And now we're talking about numerical data. So now we're going to be dealing with means questions, okay? And just as an overview so that you know where we're headed, okay? And I'm a little bit foggy on, I think 7.4 is the one we kind of brush over. Usually I run out of time, and you can read it on your own, but we'll skip it, okay? So 7.1 is inference for one numerical variable, so one mean. Okay, and let me see. Yeah, I'll use the same titles that they use. I checked it and then I promptly forgot it. One sample means with a t-distribution, of course. So one sample means with the t-distribution. Okay. So what I did was I allocated 2 whole days to 7.1. And the reason I did that is because we have to introduce the t-distribution, but also this kind of new calculation and a couple of other things. So we'll spend some time here, and then the rest of the sections will move quicker because they just build on 7.1. Okay, so we have to introduce the t-distribution, right? So this is another distribution. So we've seen the Z distribution and we've seen the chi-squared distribution so far, right? And so now we're talking about the t-distribution. Okay. And so then once we've kind of worked through that, 7.2, then we talk about paired data. Okay, so here one sample means we have one sample and I have a mean that I want to compare to some value, right? That's the exact same procedure as we saw with one sample proportion, right? I have one sample proportion and I want to compare it to some hypothesized proportion, right? Now we're going to have some hypothesized mean, which comes from the question. Okay. And let me see if I can grab paired data. Okay. So now 7.2 is called paired data. Here is kind of a gateway to two samples. So we do have 2 samples, but the observations are paired. And there's going to be a sneaky way that we deal with that. I'm going to save that. I don't want to spoil it for Friday, for your video on Friday, right? But we basically just turn it into a one sample mean problem, right? And so 7.2 is kind of an extension. So it does have 2 samples, but the observations are naturally paired. Just like before, when you read a question, it's your job to figure out, okay, what kind of question do I have here, right? So each of these, one sample mean, paired data. So those are 2 different types of questions that we could do. 7.3 is the difference in 2 means, right? So now we have 2 samples, but the observations are not naturally paired anymore. So we can call this a 2 independent sample question. So 2 independent samples. Okay. Then I just want to check here, difference of 2 means, okay. The power calculations, we're going to skip. I encourage you to read it because it's good to know that this exists. But like I said, usually I'm a little short on time. So then I just skip to 7.5, which is way more important. Okay. I guess I shouldn't say that, but so 7.4 is power calculations. Power calculations. This one you're going to read on your own, but not tested. Right, so we can skip it. And then 7.5, what did they call it? Comparing many means. Comparing many means with what we call an ANOVA. It's an analysis of variance, and that can be confusing, that terminology, but as long as you remember and that we're comparing many means, right? So notice how we have the same flow that we did in chapter 6, right? We start with one. How can I compare one sample to some hypothesized value, right? So being generic here. Then now we introduce for means. It's possible, or it's more likely that we're going to have this paired data. So before and after test scores, for example, or kind of exercise scores or something like that. So we usually have kind of before and after. So then we have these naturally paired observations, which are different from how we deal with just two independent samples. Okay, so we're increasing how many means can we compare, and then we kind of skip through this 7.4 and we go straight into comparing many means with ANOVA. So just like the chi-squared was an extension of the z-test, right? The ANOVA is an extension of what we're going to call the t-test. Okay. So that's where we're headed, and let's start in 7.1. So 7.1 is called one sample means with the t distribution. Okay. So our questions are going to be about means, okay? And with the means, so you're going to need to have a sample mean as well as a sample standard deviation, right? Because that's how we determine spread if we have numerical data, right? And so for means, right, our questions will have one sample, right? We'll have information from one sample. Okay? We'll have information from one sample, and we will be given the sample mean and the sample standard deviation. Now, sometimes these questions are a little bit sneaky because you know how to calculate the mean and the standard deviation, right? I don't want you to calculate the standard deviation by hand, right? Use your tools. So use Excel, use R, use an online standard deviation calculator, and probably even a means. I know you can calculate the mean. It's just the average. So I'm not concerned about that, right? But just make sure that you don't spend time doing manual calculations. That's silly. Okay. And so sometimes you'll be given the data and you have to find the mean and the standard deviation, right? But these are sample means and sample standard deviations. Okay. So our questions will have information from one sample, and you will be given the sample mean and the sample standard deviation. Okay. So what are some of the things that we need? Let's start thinking about a confidence interval, right? A confidence interval, I'm just going to get right in there, right? So a confidence interval in general is a point estimate plus minus some critical value times the standard error of the point estimate. Okay. So for one sample means questions, what's our point estimate, right? I'm going to be wanting to learn about the population mean, right? Which is mu, right? We want to learn about how mu behaves, right? But our point estimate here is going to be X bar, right? And so you'll have your sample mean, which is your X bar. And maybe I'll clarify here because it's been a while since we dealt with this stuff, right? The sample mean is denoted by X bar and the sample standard deviation is your S. And of course, you're also going to be given a sample size, but that's true for any of these problems, right? So that's why I kind of forgot to put it on here. And the sample standard deviation, and of course, the sample size, which is your N. Okay. I realized I forgot it because I need it for the standard error. Okay, so the point estimate, if we're trying to learn about one sample mean, the point estimate is your X bar. Okay. Plus minus the critical value. The critical value, I'm going to leave it kind of a little bit I don't know, secret. I'm just going to call it a T star. Okay, so remember, we're going to be using the T distribution. So it's fair to say that there's going to be some T star, right? Some critical value, right? And we're going to talk about T. So that's why I'm just introducing it, and then we'll kind of build on it later. And then the standard error of the point estimate, well, the point estimate here is X bar. So the standard error of X bar is S over root N. Okay. What's nice about means questions is that standard error stays the same for both confidence intervals and hypothesis testing, which was not true for proportions, right? If we were doing a hypothesis test for proportions, then we use the hypothesized proportion as opposed to the sample proportion, right, which we used for confidence intervals. So proportion questions are, I want to say, a little bit harder that way because we have to keep track, whereas now this is always going to be the standard error for X bar. Okay. Even our assumptions or the conditions that we have to check are a lot simpler, right? And so our sample size has to be larger than 30 typically, because then we can assume a normal distribution. Okay. So our conditions that we're going to check are really simple. And so usually I don't even really bother because we're just going to do this test regardless, especially if we have a large enough sample size, then it doesn't really matter. But our main conditions that we should be checking are, do we have a randomly selected sample? All right, and that's for the independence condition. And is our sample size large enough? And that's for the normality condition. And the large enough is typically 30. But if you come from a distribution that you think is normal looking, or you kind of believe that it came from a normal distribution, then you can go down as low as 20 and still be fine. Okay, so these conditions are kind of wishy-washy, and they're not something that I'm going to focus on. But it is good to know that there are conditions here, right? And so the sample size is large enough and I'll put large enough in kind of quotes here, and that's for the normality condition. In general, n greater than or equal to 30, right? Or it could be even smaller, or as low as 20 if the population is approximately normal. And I need one more line to keep it on the same page, so I'm going to bump it up. Is approximately normal. Or it's safe to assume that it's approximately normal. Yeah. So I'm kind of speeding through the central limit theorem. So this is the central limit theorem. Okay, and so here by the central limit theorem, which we introduced for proportions, and so we have the same kind of theory behind it, but for our purposes, let's not think too much about it. Of course, the central limit theorem, you can tell by the name that it's important, right? But, and it's worth kind of looking at. And of course, the textbook kind of goes through and shows you what happens as we increase the sample size. But just like proportions, even though proportions themselves, it's hard to think of them as being normally distributed, right? But as we increase our sample size, then we can assume that that these things come from a normal distribution, and that's the same same deal with means. Okay, so the t-distribution. Okay, so for means questions, we're going to be using the t-distribution. And I'm on a new page, otherwise I would do a space. For means questions, and this is specifically for 1 sample and 2 sample means, because remember, we're going to use that ANOVA for the last section, but let's just keep it simple here. So for means questions, we will use the t-distribution to find our critical values, right, for confidence intervals. Although, right, now that we've seen kind of the critical value approach for hypothesis testing, that's another way that we could do hypothesis testing. It's classically, though, we use the p-value approach. So I'm going to stick with the p-value approach, but now I'm going to start feeding you little tidbits of how you could use the critical values. But I think most of the questions that I post for assignments and stuff use the p-value approach. So we're going to focus on that, okay? But we're going to use the t-distribution. So before we use the z-distribution, right? But now we're going to use the t-distribution to find our critical values, as well as our p-values for hypothesis testing. Okay. Now, we've already seen the chi-squared distribution that changes shapes, and I didn't show you how it changes its shape, right? But as you increase your degrees of freedom, then the shape kind of shifts over towards the center. It's still skewed to the right, but it shifts a little bit more to the center, and it kind of smooths out. And so the t-distribution is another distribution that relies on degrees of freedom. Okay. So the t-distribution or maybe I should say the shape of the t-distribution. So the shape of the t-distribution depends on the degrees of freedom. How we find the degrees of freedom depends on what type of data we have, right? So for one sample means, it's going to be your sample size minus 1, right? And that's very similar to proportions, right? It was the number of categories minus 1, right? But then when we introduced more than 2 variables, then we had to take, okay, the number of rows minus 1 times the number of columns minus 1. So we've already seen this where the degrees of freedom, okay, it depends on what type of question I have, and that's going to tell me how to find it, right? So the shape of the t-distribution depends on the degrees of freedom. In the one sample means case, the degrees of freedom, and I'm just going to abbreviate DF, is n minus 1, the sample size minus 1. Okay. So, and I can't remember if I I don't think I did in the end. I flirted with posting some notes, but they didn't really match what we were doing. So I am going to be using some type notes, and I'll post them, but I don't want you to get confused because it kind of introduces everything using the t-distribution instead of the z-distribution. Let's see here. Oh, how can I bring it into ours? Oh. Oh. Too far. Sorry, I just want, okay, this is the one I want. Oh. Sorry, I just want this for the examples that are typed up so that we can read them. It used to be chapter 5, it's not chapter 5 anymore, and that gets confusing even to me. Okay. So the shape of the t-distribution depends on the degrees of freedom. However, the shape of the t-distribution, unlike the chi-squared was a skewed distribution, whereas the t-distribution is approximately normal. Okay, and so I've got a little graphic here that I wanted to show. Okay, so the normal distribution that we're used to seeing, right? So Z follows a normal distribution, right? So normal is really just the Z distribution, which is what we're used to working with, right? We're used to working with the Z distribution. We can use the Z table, and it gives us the areas underneath the curve, and we're able to manipulate those to find the probabilities, which are areas that we want, right? So now, so this dotted line here, notice that it goes very tight on the curve, right? And we remember that these tails, they don't actually go onto the axes at any point, right? They go to negative infinity, positive infinity. And so, but that area is very, very, very small. Okay. Notice the t-distribution. The t-distribution is a little bit lifted off, right? So if you have the normal distribution like this, then the t distribution kind of comes down in the center and lifts off in the tails. What does it mean when we lift off in the tails? So how we, everything else about this curve stays the same, right? The area underneath the curve is still a probability, right? And so what we're doing is we're making the probabilities in the tail higher, right? And so here, the Z distribution, right, with more area in the tail, they're also called fat tail distributions. Okay, so, but we're just allowing for more extreme observations. So with more area in the tail, right, the probability, of extreme observations, is slightly increased. What happens is these degrees of freedom for the t are going to dictate how much area in the tail we have. Okay, so the degrees of freedom for the t distribution determines how fat the tails are. Let's start using that terminology. So the degrees of freedom for the t distribution determines how fat the tails are. In fact, as you increase your sample size, right, which really means as you're using up more of the population, right, then what happens is the t distribution becomes the normal distribution or tends towards the normal distribution. Okay, so the normal distribution is just the t distribution once we have looked at the entire population. Okay, so let's see here if I have that graphic that I did. I do? Okay, so it's hard to see because this is not in color, I guess. Weird. So we have the normal distribution, which is this darkest line here, and notice how it hugs the curve and then it goes up the highest and then it goes down and it comes and it closes on the axis, not quite closes, but it comes down and it's very, very tight on the axis, right? So what happens is as we increase our degrees of freedom, right, then we're going to decrease the amount of area in the tail, right? And so as we increase our degrees of freedom, even at 10 degrees of freedom, which let's think about what that means. How do we find the degrees of freedom? It's n-1, right? Our sample size -1. So that's at a sample size of 11, right? Is this closest curve that we have. And I need to change my pointer size, but you can see how close they are already, right? So it's not going to be a huge change, but it's more proper that we're going to use the t distribution and t-tests instead of Z for means. Okay, so here, right down here, see how close these two are, and that's just at a sample size of 11. All right, so here, this means that if the degrees of freedom is n-1 is equal to 10, then n must be 11, right? So even at a sample size of 11, the curve looks very close to the Z distribution, right? So even at n equal to 11, the t distribution is very close, right? Is very close to the z distribution. Right, and the normal is the z distribution still. Sorry, I've got like tickle in my nose. Okay, so you've got this normal distribution that we're comparing stuff to, and the reason we're doing that is because we know how the z distribution, we're very comfortable with the z distribution, right? And so what you're going to find is that, okay, so for very, very small sample sizes, your tails are very fat, right? But as you increase your sample size, then those tails are going to close down on the axis. And eventually, once we have the entire population, then we're at the normal distribution. Okay. So the t distribution, and I'll just say t dist, approaches the z distribution. Oops. As our n approaches the population size. As our n approaches the population size. Okay. So for us, we're going to need to keep track of, okay, so in order to use the t distribution, I need to know the degrees of freedom, but the degrees of freedom here is just n minus 1. Okay. And so what I want to do is I just want to look at the t table, which we've already seen. We used the t table in the past to find the critical values for z, right? So we have already used the t table. I think it's like table C in that those tables that I posted, but I'm going to bring it up here. So we've already used the t table to find critical values for z, right, which we're denoting as z star, right? But now we're going to use it for t's. But now we will use it for t's. Okay. So where are those tables? Table A. Okay. So we've already used this table to find our z stars, right? And what I want to do is I'm going to see if I can maybe screenshot all of this, although it might be tricky. And there are other t tables out there. I think the textbook one looks slightly different. I like this one, and I'll show you why I like this one. Once I have it enlarged a bit. Okay. It's probably good. Okay. I'll zoom in here. So I like it for a few reasons. I like that it has the confidence levels clearly labeled up here at the top. I like that it's shaded so that you can kind of keep track of where you are in the table. But I also like, and we haven't paid attention to this before, but it has the one-sided P and the two-sided P. So remember before, for proportions, you had to, if you had a two-sided test, which means that you have a not equal to sign in your alternative hypothesis, then you had to find your one-sided p-value and then multiply it by 2, right? that's not a lot of work, right? And notice here, the one-sided p is 0.25. If you multiply that by 2, you get to 0.5. Okay, 0.2 times 2 is 0.4. They're just multiplying by 2. It's not that crazy. But I mean, when you're working through problems and you don't want to forget to multiply by 2, right, then I find that it's a lot easier if they're both here in the same table so that you don't make any mistakes, right? But notice it's just the one-sided p multiplied by 2, right? So that's the first thing that I want to point out here, right? And so notice the two-sided p, I kind of combine those two. The two-sided p is just the one-sided times 2. Okay, but these are indeed p-values. And let me not cross out the z star. Oh, I did it again. There. Okay, so these are just p-values. Okay. So let's go back up here. We have some degrees of freedom. Once your sample size doesn't change, right? So once you have a sample size that you've been given, that's your sample size, right? And so once you have your degrees of freedom, which is your sample size minus 1, then you have to stick to that row, right? And so your degrees of freedom, oops, your degrees of freedom will be one value for the entire question. Will be one value for the entire question. Right? Degrees of freedom is equal to n minus 1. Okay, so once you've found your degrees of freedom, you have to stick to that line, right? You ignore all the other lines except for the information in the margins, which we'll use. Okay. So once you have your degrees of freedom, right, you ignore all the other lines. You ignore all the other lines. Yeah. So for example, if I have 12 degrees of freedom, then I can ignore everything else and just focus on that one line. Okay, I'm going to erase that because that might be confusing later. I want you to have it. Okay, but once you have your degrees of freedom, then that's the line that you're stuck on. Okay, what I want you to see too is notice how these values, right? These values are not probabilities anymore. The probabilities are down here. Okay, these are critical values, right? Technically. And so these are just cutoffs. These are T's at each point. Okay, notice that they're all positive, and that's just because we have a symmetric distribution. So if you have a negative T, then it would behave the same on either side. So we don't need two tables anymore. Just like the Z, it was a little bit excessive to have two tables, but because we use it to learn about the distribution, then it's helpful. But we really only need one side, and then we use that symmetry to know about the other side. Okay, so the table entries, so here I'm just going to talk about these guys in general. The table entries in the t-table are critical values. And I'll just clarify, instead of probabilities. Okay. And so we only have the positive t's, okay, which means that we would end up taking the absolute value of the t or of the calculated t that we're going to end up having, but we use the positive value and the symmetry, and then we can use it for negative values as well. Okay, so the table entries in the t-table are critical values. Only positive values are given since negative values behave the same way by symmetry. Okay, so what I want to do is I want to use the Z star line, because that's exactly what we're used to working with. Okay, in fact, there are some terms that I like to kind of play around and see what people kind of do the best with, but also there's a lot of backlash from the department. They're kind of old school. Some of them, they didn't like it when I only use the t-table, because we could have done all our previous questions with just this table, and I'll show you how. I'm gonna just grab, where are the tables here? I'm gonna grab this here. Copy. So here, I'm gonna ... Okay. If we focus on the Z star line, okay, then what this table is telling me is that when Z is 0.674, the area in one of the tails is 0.25. Okay, so that looks like this. And I'm going to try to make my normal distribution as big as I can, so that I can show as many values as possible here, but I think you'll get the idea. So of course, it's centered on 0. Z is centered on 0, and same with T. Okay, and so let's do green. So we'll start here. And what it says is, it says that at 0.674, the area in the tail here, and I'm going to do it like this, is 0.25. And if I look at negative 0.674, which is on this side, negative 0.674 by symmetry, the area in this tail, I didn't do a very good job there, is also 0.25, which means both tails add up to 0.5. Okay. Now, let's go to one that we're kind of familiar with, right? 1.645. If I go to 1.645 of Z, right, then this table, 1.645, tells me that one of the tails has an area of 0.05, right? 0.05, which means that also negative 1.645. Oh, that's not very symmetric, is it? One went up to, I gotta fix that. That's crazy. Let's see if I can do it. Okay. negative 1.645. There. It doesn't look very beautiful, but I think you're getting the idea. Okay, and so what can we do when we live in a shoe? No, here 3.291, that's as far as this table goes. Now remember, we're used to 3.49, so our Z table goes a little bit further, right? But the idea stays the same. So it's possible that we go off the table, but what happens, right? We still know something about this 3.291. And that is that the area in one of the tails is 0.0005. Right, so 0.0005. And if I go to the negative side here, negative 3.291 also has an area of 0.0005. So then times 2, 0.01 or 0.001, right, is the two-sided p-value. And notice that the area between these two, right, the area between these two values is going to be the confidence level, right? So if I had kept, which I did not, oh, that's the wrong, I saw tab something, right? But if I had kept these guys, and maybe I'll overlap them, paste. I cannot, okay. Okay, let's see here. Let's see if I can move all of this down. I've managed to make a mess here. What if I do this? What if I crop it? And I put her there. Okay, they're a little bit shifty eyes. There. I did it. Dun, 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 dun. Okay, so then the area between these two is 99.9%, right? So if I want a 99.9% confidence interval, 3.29 would be my critical value, right? Plus and minus, right? I want that, that central area. Let's go to one that we're more comfortable with, more familiar with, right? 1.645 we said was here. If I have 0.05 in each of the tails, that means I have a total of 0.1 chopped off, which means I have 90 in the middle. And that's why 1.645 is our critical value, right, for Z star if we want a 90% confidence interval, right? And so so here I want to write the matching 90%. So from here to here, I have 90% confidence interval. Between 0.6745, that's if I want to make a 50% confidence interval. You'll never do that. That's so weird. Why would you only want to be 50% confident? I have no clue. Right, and then here between these two values, right, this is why we have a 99.9% confidence interval. Once you've spent enough time looking at this, you can see why, okay, either you're 90% confident that the hypothesized value is within this interval, right? Or if the p-value is greater than 0.1, right, or less than 0.1, that means that you're outside this interval, right? So you can see this connection between confidence intervals and hypothesis testing. That's not something that I'm expecting you to see right now, but it will start to come, right? And this is the relationship, but that's why the confidence interval, we can only use it for two-sided tests, right? As soon as we're only doing one-sided tests, the confidence interval and the hypothesis test, if you're on the verge, will not necessarily give you the same conclusion, right? But for two-sided tests, they are confidence intervals, essentially. Okay, so our T's work the exact same way. And notice that if we're looking here really close to Z star, so if we have degrees of freedom of 1,000, then these values, right, if you compare the two, 1.037 and 1.036, they're very, very close to each other, right? So you could use the Z, but it's more proper to use the degrees of freedom. Notice that also you have towards the end, so in the beginning you have, I think 1 through 30 listed out as your degrees of freedom. But if you have to choose your degrees of freedom between two values, you always round down. Okay. So note, and I'm going to see if I can, right, your degrees of freedom after 30 so here, oops. We will need to decide on degrees of freedom. For example, if you have 48 degrees of freedom, then what are you going to choose here? If you have 48 degrees of freedom, you have the choice between 40 and 50. It's going to be tempting to go to 50 because you're so close to 50. But what does that mean? That means that you're assuming that you have a sample size of 51 when you actually only have a sample size of 49, right? If your degrees of freedom is 48, then you have a sample size of 49. And that doesn't feel like a big deal, right? But especially if you're choosing between 100 and 1,000, it might be really bad to assume that you have a sample size that's large enough to be give you 1,000 degrees of freedom when you really only should be using 100. Right? Notice that these values don't really change, right? But it's just how we're going to deal with these is we always round down. Right? So we will need to select the appropriate degrees of freedom. Okay. And we will always round down. And we will always round down. Okay. And I'll put in brackets here, otherwise we assume we have a larger sample size than we actually do. Right, so for example, if your N is 49, right, then your degrees of freedom is 49 minus 1, which is 48, right? And then what we say is, but using 40 degrees of freedom. So here's how we follow through, but using degrees of freedom equals to 40. And maybe I'll put the quote around here. So you always want to highlight what degrees of freedom you're using, mostly because Oh yeah, so so you always round down, even when for some reason it hurts. Let's say you have 990 degrees of freedom. Oh, I have to round down to 100, right? Because I don't have 1,000, right? You have to exceed it. And so even when it's, I don't know why it's painful. Notice there's really no difference here, but for some reason it just feels painful to have to round down if you have, so even if degrees of freedom is 990, we need to use degrees of freedom equal to 100. We need to use, and of course, software would, oh yeah, so then if the sample size is over 1,000, then you use 1,000, right? It's not until you have the entire population that you're allowed to use Z, but that's never going to happen. If you have the entire population, why would you need to guess about what's going on, right? And so, so if it's 1,000, that's the largest degrees of freedom that we'll use. So even if the degrees of freedom is 990, we need to use, oops, right, in eraser, use degrees of freedom equal to 100, right? If degrees of freedom is, let's say, 10,000, we need to use degrees of freedom equal to 1,000, right? Even when it's, I always feel like, oh, what a waste. It's not, it doesn't matter, right? But you always round down because otherwise you're assuming that you have a larger sample size than you actually do. Okay. So that's one of the things that, of course, is going to be a mark, right? Is what degrees of freedom are you using? Are you using the appropriate degrees of freedom? Okay. So let's see here. If we focus on our confidence interval, then our critical value is not going to be that bad to find, right? Why? Because we find the critical value the same way that we did for Z star, we find our T star, right? But now we have some degrees of freedom and we're going to use that line instead of our Z star line. Okay? There's a lot going on with the T distribution, right? But once we have a handle on the T distribution, then we're going to be just smooth running here. Okay, so so that's why I wanted to take today to really talk about the T distribution and the shape and stuff like that, degrees of freedom. Okay, so to find a critical value, right? To find a critical value, which we're going to denote T star, we use the degrees of freedom line and the confidence level in at the top, and the confidence level at the top of the table to find the critical value. Or maybe I already said to find the critical value. So we use the degrees of freedom line and the confidence level at the top of the table. So for example, find T star for a 95% confidence interval with n equal to 57. So what's the first thing we have to do? We have to say degrees of freedom is n minus 1. So the degrees of freedom is 57 minus 1. And of course, this is one of those few times where you don't have to stack your calculations because they are so basic. So in fact, I'm going to save us some space here and I'm going to go across, which is not something that I'm okay with you doing in general. I want you to stack your equal signs, but here it's such a simple calculation that I'm okay with it. So we have 56 degrees of freedom, right? So if I go to my table and let me see here, I did a little chopped version, but I'm going to need to do another one. And I'm going to need the top of that as well. Paste. Okay. I think we've got it kind of lined up. Okay, so boom, boom, boom. All these values, of course, continue. So now, if we have 56 degrees of freedom, then I go to my table and I'm trying to choose, right? What we just decided was I'm going to have to use 50. So if I'm making alterations here and I can't just use these degrees of freedom straight out of the bag, then I have to say that, but using degrees of freedom equal to 50. But using degrees of freedom equal to 50. So that means that I'm stuck on this line here. And what am I doing? I'm moving out as I increase my t's. Of course, it behaves the exact same way that the the z distribution works, but now we've got just a little bit more area in the tails, but that's the only difference, right? Notice the difference between a z star of 1.96 and a t star of 2.009, 1.96 and 2.009, pretty much the same, right? So there's not a huge change happening here. And so I want you to kind of look at those and say, okay, well, at these higher degrees of freedom, it's not really that big of a difference. Okay, and so here, if I want a 95% confidence interval, right, then I'm going to be working here. Before, we would have used a z star of 1.96, right? But now I go to my t star, right? So t star, and sometimes we have the little degrees of freedom as a subscript. Degrees of freedom is the t star 50. And sometimes we have it a follow-up with the alpha level, but let's just ignore that for now, is 2.009. Okay. So that would be our critical value. Okay. If we are doing a hypothesis test, what we're going to do is very similar to the chi-squared test, which also had these degrees of freedom that we were working with. But what we're going to do is we're going to find our calculated t. So we're going to calculate a t, and I have not told you how to do that yet. So we'll save that. But you're going to have a calculated t, and you're going to try to place it somewhere along this line, right? And so it's increasing from technically 0 to infinity, right? But we only see a certain portion that we're interested in. And so we try to place our calculated t somewhere along this line, and then we can use that to find our p-values. Okay. So here, what I want to do is I'll put that back on, but I want to just copy this so that I can have a fresh table again. So copy, paste, good. And I'll put those highlights back on here. So 95% confidence interval. Oops. And 50 degrees of freedom. Sorry, I'm getting there. There we go. Okay. So that's if we're doing a confidence interval. Okay. What if we're doing a hypothesis test? Okay. And so if we are conducting a hypothesis test, we will calculate a t as our test statistic. We will calculate a t as our test statistic in step 2, which is do the test, right? Calculate whatever test statistic is appropriate for that type of question. Okay, so you're going to have some calculated value of t. For now, let's just say that t is 2.5. Just like Z's, we suspect that that's large, right? But the t, we're allowing for slightly larger values of t, so we're going to need to find our p-value. Right, and notice how I'm completely ignoring everything else, but we are going to do a full hypothesis test and a confidence interval next day. Okay, so we are going to go through this, but I just want us to be comfortable with the t table so that we can jump right in next day. So we're going to calculate a t in step 2. So for example, say let the t, and I'm going to show the calculated be, and I'm going to make it negative just to show you guys how it works, right? Because we only have positive values in the table. So the t calculated is negative 2.739. Now t, to match the table, notice the table has, oops, didn't think, I thought I was in pointer. Notice the table has 3 decimal places. So then we use 3 decimal places. T should have 3 decimal places to match the t table. Right? Z, we rounded to 2 decimal places because our Z table only uses 2 decimal places. Right? So you always want to match the table that you're using. Okay, so the t calculated is negative 2.739, right? Which means that I need to take the absolute value to find, let's let the degrees of freedom be 56, but let's let it be 50 again, right? To find the, let's say the one-sided p-value, we take the absolute value of, and maybe I'll say one-sided or two-sided, just depends on how you read the table. To find the one-sided p-value, we take the absolute value of the calculated t and try to place it. Well, I don't think we try, we just do it, I guess, and place it where it falls in the t table. So place it where it falls in the t table. this will allow us to find a range for the p-value, the one-sided or the two-sided p-value. This is the same as the chi-squared, right? So we're not unfamiliar with this, but this gives us a range for the p-value. So how we write it is I'm going to find a range for my t. Okay, so first what I do is I write my calculated value in absolute value brackets in the center of my page. And then I'm going to jot down what the values are surrounding this calculated value. Okay, and so here, let me make this bigger here. I've decided I have 50 degrees of freedom. So maybe what I'll do is my t calculated was negative 2.739. The absolute value of that is, of course, 2.739. And I know I'm all out of time, but I just want to wrap up this one idea. Okay, so 2.739. Once I take the absolute value, then I try to place it somewhere here. 2.739 would be somewhere around here, right? 2.678. So what I'm going to do is I'm going to wrap these around, right? 2.678, and it's less than 2.937. So see how this is how we show that this is what we found our range to be. Then below that, I write my p-value. So if I want the one-sided p-value, for example, I write that here. The one-sided p-value is going to be around, or sorry, the range for that is going to be, I just want to give myself a little bit more room. If I trace back for my one-sided p-value, I'm on this line here, and notice that I have to read these from right to left because they're smaller to larger, right? So then my one-sided p-value is somewhere between 0.0025 and 0.005. Okay, I know I'm all out of time. So sorry. We'll pick up here next day, but I'll stop this recording. If you have any questions, let me know. Otherwise, see you on Thursday.